Good afternoon, everybody. We are now in our fifth day of our course, short course. This is the fifth class, and as I have promised to you, today we will be presenting the last derivation of the Schrödinger equation, a derivation based upon the notion of Langevin equations of quantum mechanics. We will show basically that we can find stochastic support for the quantum mechanics Schrödinger equation, and by means of this stochastic support, we will be able to make a number of simulations. I will show you the simulations, and these simulations will show to you a number of results regarding the interpretation of the theory. So I think this will be interesting to close the circle, if you will, regarding the derivation of the Schrödinger equation from first principles and the consequences that we can draw from it. Okay, let's begin. We are searching a Langevin equation for quantum mechanics because we have derived the Schrödinger equation based upon a stochastic approach. But when we did that stochastic approach, I don't know if you recall that, but we have used at some point an average. In fact, this average was, for instance, for things like that. And we call this if you use a vector notation, this was the composite velocity. And also, we have used this average and to make it equal to the value of the constant d, which afterwards we have assumed constant in the diagonal constant. Okay, but the fact is that this average takes away the main elements of an stochastic approach, which is, of course, the stochastic behavior. We, of course, we will end up, if we do that, with only a theory that also encompasses the averages that we have made. And in this case, we are searching for what I have called here a concrete stochastic approach, because we won't make any average, at least in the Langevin equation, we will have no average after all, and our equation will be able to show in a concrete way the behavior, the stochastic behavior of the quantum mechanical system. Okay, and this is important because I have a number of elements of the interpretation that I want to stress, and they can be stressed only in using a theory that does not make such averages. So our questions, of course, our first question, of course, is where do the fluctuations appear in mathematical terms? Because if you look at the Schrödinger equation, you won't find there any kind of stochastic term or anything of the kind. And if you want to understand the Schrödinger equation based on a stochastic approach, it's the only way that I find reasonable is to search for an equation that is under the Schrödinger equation. So you have here the Schrödinger equation, and you have an equation that is under in the sense of being more fundamental, and from which the Schrödinger equation appears as some sort of an average. Of course, we are being guided by this result that was already proved when we had made the stochastic derivation. Okay, so we will try to show that this equation, this stochastic support for the theory, is exactly a Langevin type equation, which may give us all the quantum mechanical results usually obtained by using the Schrödinger equation. Okay, let's begin by presenting the Langevin equations. I will be using here a one-dimensional approach, but of course, it can be extended for more dimensions. And the Langevin equations that I will be using are these two here with these two constraints. In fact, these constraints are related to the fact that we don't have memory and that our fluctuations have zero average. Here is the fluctuating term, and we don't know the appearance of this term from the beginning, but we know that since we are in the realm of a Langevin equation, we must have a fluctuation term together with a dissipation term. This is a dissipation because it depends on the velocity or the momentum. There is no difference here. This, of course, is the Newtonian force. And this is without these two terms here, the system of equations is just equal to Newtonian mechanics. Okay, what we will be doing is trying to find, while deriving the Schrödinger equation, we will try to find the mathematical expression for this term. So let's begin our approach. The first thing that we will do here is to discretize the time. Time becomes discrete. And also the equation. We transform this first derivative in a derivative that is something like that. Pn plus 1 minus Pn over tau, for a small tau, of course. This is just gamma P, which is Pn, plus phi 1 Q, plus the fluctuation term here, which depends on your own. So I may pass the tau to the other side, and I get just 1 minus gamma tau Pn plus phi 1 tau plus tau t. And this is what I'm calling A here. This is A, as you find here. And we have to make, since we have here a Dirac delta function, we have to make this kind of transformation so that we can still have a constraint of this kind, which now we have here a Kronecker delta function. Delta symbol. Okay, so our target equation is this one. What we will do in the following? We will iterate over this equation and use these two results here to calculate our results. Note that when iterating, we will find, of course, P1, P2, etc. And from these p's, the momenta, we will build our sum of random variables, which is the connection, the obvious connection with the central limit theorem derivation. Okay, let's go. I said all this for you because I want you to be to understand what we will be doing in terms of the previous derivation. Okay, so again, as we did with the central limit theorem, we are considering a fiber on phase space. That is, we are taking here a small region in X in Q, and we are considering our sample space being given just by the variation of P over this fiber. Okay, let's begin. So I write here again the equation because it will guide us on our quest for the Schrödinger equation, or something that we know that we can use to get the Schrödinger equation. We don't need to go up to the last situation, the last derivation, because we know that after certain results, the Schrödinger equation is just a natural result, natural consequence. So, as I said, if we are assuming an ensemble simulation, what we have is in configuration space. So this is our approach. Okay, now we can, as I said, iterate over n, and for the first n equal to 0, we get just this expression here, just put 0 here. For the second n equal to 2, we get this more involved expression, but we can show, and it's easy to show, just looking at the previous results, that for wait, tá. Mas isso está mexendo, alterando a minha apresentação? Ah, tá, entendi. I was told here that we are experiencing some technical problems, and this may change our results in terms of the presentation a little bit. So don't bother with that. We will soon get back to our original situation. I hope you still hear me, and I will continue to present and hope that we can get better results soon. So continuing the presentation, we are iterating this equation. We get for the n equal to 0, this first equation. For n equal to 1, this second equation. And when we look at these equations, we know we may prove that for an n, a general n, we have this situation here. Note that now, just for simplicity, we may assume that our initial momentum is 0, just to get rid of this term. And here for the n plus 1 term momentum, we have just a sum of some terms here. And in fact, we will assume that our Pn is just a sum of random variables. And these variables are random because they are based on a random term represented by this one that I have just written here. Okay, the same thing we have here. Okay, Now we will define a characteristic function. Again, this makes the connection between the present approach, the central limit theorem approach, and the characteristic function approach. So I will stress here that we are in a situation in which the derivations begin to connect with one another in a very strong way. And of course, as I have already said, this characteristic function is taking over fiber because delta Q is made and Q are made fixed. Okay, continuing here, we can make averages. So we have these results. This result here is the one most important one. Now we want to get average like this. So let's begin to make this average. We can take the average of that term. Let's see. Look, this term does not depend upon the variables. So its average is just itself. And here, when we make an average, we can use that this average is 0, as we have shown, presented. And so this term will give 0, and we will have just this result as the average of the random variable. The second result we obtain when we put together, we multiply these two random variables. The result that we get is just this one. We again make an average of all of them. Remember that this average gives just n L L, which is 1, the Kronecker delta. And so we end up without this term and these two terms which are represented here. We may, from these two terms, we may find the variance of the problem. And look, the variance of the problem is connected to this term here. And we know that from our derivations, previous derivations, that the variance in momentum is related to something like this. But let's find this doing calculations, okay? Again, this time, this is interesting to show too. We can divide this term for this time. And what we are saying that in the limit when L goes to infinity, this term will survive because of this term here, which is dependent on tau 2, okay? But it is to the power of 12. Okay, let's go to continue. If we now make our average upon this function, I won't go into the details. This is the average, but this average, note that this average is just the integral of the exponential of each random variable. Okay, this is the average because, of course, if you have something multiplying the f, the average of this thing that you multiply is just this equation. Okay, so this is what this means. This means that we are taking the average of this term. This is the meaning of the characteristic function. And when we do that, we get an expression with a quadratic term and an expression with an average here. Of course, we can now look that we are obtaining here the results for the small cap characteristic function because it is related to each independent random variable. Now we may find the characteristic function of the whole process, which is the product, as we had said, the product of these infinitesimal characteristic functions, and we would then find this result that is represented here, in which it is important to say, look, if I make a product here, these terms will sum, and using the result that I have obtained for the average of WL, I end up with just this result for the average of P, which is the sum of the random variables. Of course, I have used this index here because I'm doing at this point a finite sum. Of course, what we will do in the future is to make n goes to infinity. Okay, the other element here is the Bn, and the Bn is possible to be obtained by just calculating this result here. This is so because, of course, all the elements here, if you multiply, since they are represented by exponential, we will have just a sum of these elements with respect to L. So we will have a sum in 2L, A to 2L, and a sum in A to L because of the result for the WL, okay? So there is no difficulty here. So we may now proceed by making an inversion in this expression here. This inversion will give us this function, which still depends on n. Note that n is inside this element here. And I can finally make the limit to as n goes to infinity, but we may make this limit, and remember that we are summing something of this kind. 1 tau 12, and here a 12 will be just 1 minus gamma tau 12. Okay? Okay, so when we do that, this is the same. To make n goes to infinity is the same as to make tau go to 0. Okay, and we will make this sum here and express this sum in terms of tau, because R depends upon tau. Of course, tau is just 10 over n. So since t is finite, n goes to infinity, so tau must go to 0. Asymptotically. So we have these two expressions, and when I do the sum, this is an expression of progression, a geometric progression, so it's easy to calculate. We can write this in this term here. I'm keeping the term with n because I'm summing geometric progression, a finite geometric progression, and the result is just given by this. The other result, which is for this one here, is given by the following result here. Okay? Actually, it's not correct what I have said. This result is just the limit when I make gamma goes to 0. Tau goes to 0 here. When I make tau goes to 0, and also n goes to infinity, note that this is just the expression of an exponential, okay? And then we get this exponential here because of this calculation. Okay, we end up with this result for this term here, which is related to the variance. And we end up with this term here, for which I didn't present the calculations, but they are similar to those that I just presented here. And so we also have this result. I can now calculate this situation for asymptotic time when time goes to infinity. And when I do that, let me show, when I do that, this term here will give the following results that are shown here. I find that unknown term, which appears in the fluctuation term, the stochastic term, the Longev equation, is just the momentum fluctuation value that I have already found in other derivations of the quantum Schrödinger equation. I also make this connection, it is the usual connection. And with this result, we just get, now without any n here, because this is the asymptotic expression. So I get exactly the same result that I have obtained previously in when I was doing the stochastic, the entropy derivation, and also the central limit theorem derivation. So this makes a very important connection between the two derivations. I know that from this expression I can get the Schrödinger equation, and I think that this derivation is important for two main reasons. The first reason is because it is when you go into the details, it is quite connected and explicitly connected to the central limit theorem and also to the characteristic function derivation. So I think that these derivations in a way put the other derivations into contact even more explicitly than before. But the second importance that I think that this derivation has is the very Langevin equation that we have just found. Because if you note, this is an equation, unusual equation for a Newtonian particle, but which is not Newtonian because, of course, there is a term related to fluctuation and also derivation, dissipation. Sorry, I am a little bit tired, exhausted from this week of classes. Because when I do that, and mainly when I make the discretization of this equation and get these results here, I can now make simulations of these results. Indeed, it's very easy to make such simulation. I will use the mass equal to 1, okay? Little tau here and a tau here. Okay. So I will show you now an app program that I have written, and that will show you the graphic situation of quantum mechanics, and we will try to get from these simulations some of the results that we have already been assuming and using as an interpretation of quantum mechanics. As a last result, I can calculate the same expression that I did for the random variable to the second and first degrees. Now I can calculate to the third power. And when I make the summation, look at what happens. That remains, my God, I wasn't remember that I had this term. But if you can see this, you can see that in this situation, if I make tau goes to 0, this term disappears, this term disappears. But note that we remain with a tau in the numerator. And a tau, because I can cut this with this term, this becomes 2, but this one still remains. And the fact is that when tau goes to 0, this term goes to 0. And this, in fact, is the content of the central limit theorem. This result is important because this is the content of the central limit theorem. The central limit theorem is saying that if you want to keep these terms, they won't be relevant when you make n goes to infinity, or the same thing, tau goes to 0. Because from this term on, with respect to the degree, you will always have a tau in the, or something greater than a degree greater than 1 for tau in the numerator, and when you make tau goes to 0, this will disappear. This is the content of the central limit theorem. Okay, so the Langevin equations for quantum mechanics can be expressed in this way that I'm showing to you in the screen now. What we will be doing now is to use an application, a program, which make the dynamical development of this equation. So what I will do now is just end this presentation with the PowerPoint. Let me go back to the presentation here, because I will now present the program that I have just made. Give me just a moment. I will be showing the program to you in what follows. I will load the program. I didn't load it before because I have a computer with not much memory. While the program loads, I will be loading the presentation. Oh my God. The fact is that, as you will see, some of the most important elements of the interpretation can be now stated in a way that you can see by means of the simulations that they indeed apply to the actual quantum mechanical problems. Of course, I have made these calculations and simulations for only two systems, quantum mechanical systems. One was the harmonic oscillator, and the other was the Morse oscillator. So the program is already loading. Just give me a moment. There is a discussion related to what can we see in the realm of quantum mechanics, which is very ancient. In fact, it was one of the first discussions that we may find in the literature about the historical development of quantum mechanics. The discussion took place between Niels Bohr, and Schrödinger, and the discussion has its origin because Schrödinger defended that quantum mechanics should have what he called Anschaulichkeit, visualizability, but this is not very easy to translate. But the Planck was defending that quantum mechanics, as any other physical theory, should be connected to a way that we can see what is going on in nature. And Niels Bohr, of course, was completely contrary to this perception. And there is a historical this is represented in the literature. You may find this in the history of quantum mechanics, that Schrödinger was in Copenhagen to visit Niels Bohr, and Niels Bohr received Schrödinger already in the train station and began to discuss with Schrödinger even at that point. And Schrödinger at some point became very tired, get ill, and when he was in his bed, being cared by Bohr's wife, and very bad with respect to his wealth, and Bohr was sitting beside him, trying to convince him that he was right and Schrödinger was wrong. But the fact is that Schrödinger was a defendant of the tenet that physics in general. Oi. Não, o slide eu sei que sumiu, mas porque eu estou vendo aqui, é porque está carregando o programa e por alguma razão está demorando um pouquinho para carregar. E com isso, ele travou a minha tela da conferência, mas ele já está destravando aqui, tá? Agora, a câmera não está me mostrando, então. Tá bom. Daqui a pouco volta. Pronto, agora talvez vá voltar agora. Vai voltar agora. Ok. Sorry for that. I was loading the program when I was loading it, I think it make the program stop showing my webcam. I will now share the screen of the program with you. You may find the program here. I call this program the El Quixote stochastic simulation. I think those more that value the literature may already understand why I'm using this name, El Quixote. And what I will be showing here is the simulations of two physical systems, the harmonic oscillator and the Morse oscillator. So let's see what happens when we have the harmonic oscillator for the n equal to 0 quantum mechanical state. We will be doing a simulation of the single system type. And we will show that a particle, because what we will be seeing here in the screen is a particle, mainly in this screen here. And we will see that these particle in a time window will just restate the probability density function of quantum mechanics. What I'm trying to show you now is that corpuscles or particles can give a wave-like behavior even if you have only one particle, if you look upon this particle for some time, and of course if this particle moves in a random way. So I will be using 400,000 points in each trajectory. Of course, there is only one trajectory. So we are here again in a single system interpretation or simulation. I will also plot the exact probability density function, okay? And so let's see what happens here in the phase space, on the phase space, and what happens here with the probability density function as the simulation goes by. So look at this point, at this screen, to see the probability density function upon configuration space of a single particle moving in a random way, and also on this screen for the phase space movement. You will see the phase space movement as a very quick movement because I have to buffer the screen, because the screen occupies much memory, so I can make the simulations one fluctuation at a time, because there are, of course, 400,000 steps, and we would be here for the next 4 days to await for the simulation to stop. So let's start the simulation. What's going on here? Why it's not showing? I forgot to write here dynamic and here dynamic. Doesn't matter. I will wait the simulation to end, and I will do it again, clicking in this dynamic and dynamic, because this is the dynamic way by which we can make the calculations. This is the best way to see the dynamical evolution of the quantum mechanical system as represented by the Olavo equation. So this is the end of the results. Look, I will assume a greater point. Here is the phase space probability density function. It is a circle upon phase space because the fluctuation is just 1/2, and so it introduces no structure on the fluctuation behavior. And here is the comparison between the exact solution of the Schrödinger equation and the result of the simulation. But now let me choose the dynamical simulation. Let me clear this graphic here. This one, I will just begin. You will be able to see a transient part of the problem when the particle, of course, there is a transient part because the particle begins to fill the configuration and phase space, and so, of course, the probability cannot begin as just being with this format. This format is just the asymptotic result when we look for the system for a sufficient large time window. So let's see that. Okay. Look at what happens here for the probability density function. This is the representation of the transient situations. Look at that as we go on in the trajectories, the steps, the points in the trajectory, the behavior of the particle. We are approaching the asymptotic result, which is just the quantum mechanical probability density function, which is obtained, of course, from a wave function, which is the psi. It's almost ending. Let's compare this with the exact function that we get from the solution of the Schrödinger equation. It's almost finished. My computer is very bad today. I hope I can recover from this. Let me see what happens. Some days are very difficult indeed. And I will just continue. This is a feature of the Windows. The common language runtime becomes suspicious that something is wrong because I'm not answering to the calculations. So look again, the relation between the simulations and the exact result is very, very good. Okay, we can do that for other quantum mechanical levels, other quantum mechanical states of the harmonic oscillator. Let's just see what happens for n equal to 2. Let's make this only once. Again, the probability density function. This is the probability density function. It is completely different from the probability density function of the ground state, of course. And what we get is the behavior. Look what happens as the system fluctuates, and feel the configuration space. On your right is the phase space representation, and in the middle you have the probability density function representation. If I want to get better results, I will have to use a greater number of points in the trajectory. I can do that, but it will make the simulation to be longer. So I think it's sufficient to have a picture of the situation, okay? So this is the result that you get when you make the simulations. You can also do that for another system, quantum mechanical system, which is the Morse oscillator. I just use this. And for the Morse oscillator for single system, one trajectory, of course, and 400,000 points in the trajectory, I can again make a phase space portrait of the random system and also represent here the probability density function. In the case of the Morse oscillator, we remember that our variable is represented in terms of a radius that goes only up from 0 to infinity. So this is why we are getting this expression here. So let's make the simulation again, now for the Morse oscillator, and see if we find a connection, a good fit between the quantum mechanical exact result and the ground state of the Morse oscillator. Again, you have a transient behavior, and after this transient behavior, because we are considering a time window, the simulation is just showing for you the time window. What you get is just the fit of the quantum mechanical probability density function with respect to the simulation. Okay, so let's wait for a moment. It's almost ending, and we get the result as you see in the screen. Of course, what you see is a very good fit. We can do that for a second level. It's interesting because the Morse potential is a potential that you may have uh, the particle escaping the uh, what we would call ionization, the particle escaping the potential barrier. But in this case, it's not still very very common. Let's clear this. And let's show the second state probability density function. This is one. So let's make the simulation again. Again, I will repeat. Sorry for that. I will stress that again. We are presenting a simulation in which a single particle is moving on the configuration space and filling the configuration space with higher or lesser probability. And this is what you see in the screen. It's just the representation of this situation. For higher states of the probability density function, if you are doing a single system simulation, you have to be careful, because if you have an ionization of the particle, of course, the problem ends. So this is a situation which is in the middle of those systems that can be related to the ergodic principle. For lower states, it's obvious, but for higher states, it cannot be correct, because of the possibility that the particle simply goes away and the problem becomes destructive, as I have already told. Okay, we have seen the first thing that I was willing to show you is that we can, with a particle, reconstruct in a time window the wave-like situation that we find in the quantum mechanical formalism. Now I want to show you another thing. Let me see what I can do here. Let us show the ergodic principle into action. Let's do that for the ground state of the harmonic oscillator. Let's plot the density. I won't plot this now because it's not relevant for our approach. This appears because it is in the memory, but when I begin the next simulation, it disappears. I will simulate, but now I will simulate using an ensemble. This ensemble uses 2,000 quantum mechanical harmonic oscillators prepared in the same way. And in each trajectory, I will assume 1,200 points. Why I have to assume this? Because as I told you, as I showed to you, in fact, the system has a transient part. And I'm trying to get the part in which the system is already stable, which is what the Schrödinger equation shows to us. So I had to wait for a while. This is the while. And when this number of points in trajectory, which is just the time, because I would multiply this number by the tau. Where is the tau here? I don't have the tau explicitly here, but the tau is 0.001. So I'm waiting some 12 seconds or 12 arbitrary units here. And then in a single time, that is at the end of this time here, I make the average for each system of the ensemble. This is what I'm doing here, okay? And we will try to see if the result that we get here is the same as the result that we got using a single system approach. Let's see if this is the case. Why this isn't showing? An ensemble, and generally in ensemble calculations, it makes not much sense to see how the wave function, the probability density function evolves, because of course this is an evolution for the ensemble and not for the single system. But the evolution is quite the same as you get from the single system simulation. It is just not here to present. Okay, let's wait a little bit. The result will show up in the screen as points, exactly in the way they were shown in the previous simulations. So again, we are taking 2,000 trajectories, that is 2,000 realization of the problem, and we are weighting 1,200 points to make our average at a single instant of time. This is the ensemble calculation, and this is the result that we get. To get better results, of course, we can improve the number of trajectories to get better results here. We can show that by making the simulation again. This will use, if I'm not mistaken, this will use the previous results. Then it's the same as doing the results for 4,000 trajectories. Let's see if this is correct. I made this program some 4 or 5 years ago, so I'm not sure of all the details that it shows. Okay, it's almost there. Let's see if our results get better. They are a little bit better, look. And this is what I was telling you as the ergodic principle. It doesn't matter if you do the simulation using a single system or an ensemble. Let's do that for the second excited state. Again, the probability density function. This is the function. Dynamical simulation, 2,000 trajectories, and 1,200 points in each trajectory. The time interval is here, 0.005. Okay. So let's make the simulation. We will have to wait a little bit while the system calculates the densities. I'm not sure if you know, but the way by which you represent this simulation on the configuration space there in the screen, represented by the interval minus 4.5 to 4.5, is by dividing this interval in small boxes, and at each time the particle passes from it stays for a while in that box, you increase the box frequency in one point, one unit, and then you make the graph by making the histogram of the relation. Here you see a very good representation of the actual result. So I think I'm showing here the possible application of the ergodic principle for quantum mechanics. I can now do the same thing for a Morse oscillator. Let me do the ensemble, the same number of trajectories, the same number of points in the trajectory. Let's draw again the probability density function. I think I have to change this. This is to fit the function on the screen. I'm not sure. Just to make the comparison, okay? I don't think that this will be good because it is displaced here. But okay, let's do and see what happens. I'm not sure. I'm not sure that I have prepared these parameters here to give the exact result. So I am unaware of the results as you are. I find strange that this axis is presented in this way because, of course, the Morse oscillator goes from 0 to 3. But let's just see what happens here. It's really strange. I may have done something wrong, but okay. Here is the result. It's not the best way to show. I can probably write this in a better way. Okay. I think you have got the situation here. We get the same result for the ensemble simulation as we have gotten for the single system simulation. So I'm showing to you the application of the ergodic principle for these two systems, quantum mechanical systems. I'm not proving in general that this applies, this ergodic principle applies. But I'm showing that for at least these two systems, and in fact, I use this for the hydrogen atom and another side, and the harmonic oscillator in 3 dimensions, and the results was just the same. Okay, the next result that I want to show you is the relation between these systems and Newtonian system, what we usually call the Newtonian limit. What this represents? You may have already seen people saying that you can get the classical limit. It's usually named classical limit because if you make h bar goes to 0. But this you have to be very cautious about that because it makes no sense, of course, everyone knows that, to make each bar goes to 0 in the Schrödinger equation. So when can you make the h bar goes to 0? And this answer is very easy here in this formalism, because in this formalism, you have a Newtonian-like equation, which is the Langevin equation, which is different from Newton's equation just because of that gamma function, which appears both in the dissipation term and the fluctuation term. And when you make gamma goes to 0, you make gamma to go to 0, this parameter, what you get is just the Newtonian system. Let's see here in this panel. if this is true. I'm now using one trajectory, a single system approach, of course, and I'm using just 65,000 points in the trajectory. Note that the gamma is being put is 0, and I'm using a very small time interval, because I'm not, of course, making an integration of Newton's equation. I'm making the simulation of the Langevin equation for gamma equal to 0. So if I don't put the time interval very small, I will get problems of error. How can I say that? The errors that will accumulate during the simulation. Okay, so look at here what happens when we simulate this. I'm not showing densities for now, just phase space movement, and of course we get just circle, a circumference. This is of course obvious, because I'm using p squared over 2 plus x squared over 2. So in phase space, this is just the equation of a circumference. But now look what happens if I begin to increase the value of the gamma. I'm not sure if I use vírgula 0.01. No, I have to use point 1.0 plus 0.001. Now I have a small disturbance of the given by the fluctuations, because gamma is very small, so I will get almost Newton's result, or Hamilton's result, if you will, but the fluctuations will become to appear. Let's look what happens. Look at the situation in the screen. In this screen, we get the trajectory that begins to differentiates itself from the Newtonian one. I can make another result by making a greater gamma, and to this different gamma, we will have more even stronger fluctuations. Our correct gamma for these states, if I'm not mistaken, is just 1. So I am a little bit far from the situation. Let's simulate again. Note that for this point, the situation becomes much more complicated. Let's put more terms here, 60,000 points. Let's assume 100,000 points, just to see what happens. Look, this is a new realization of the situation, and now you get a very different result. I can now put the usual values, and when I put the usual values, what we get is the result that we have already got before, which is connected to the true quantum mechanical probability distribution function, density function upon configuration space. Another situation that we can represent here. Oh, before doing that, what I'm showing to you here is that you have a continuous passage from Newtonian mechanics to quantum mechanics. This is very important, because now think about what you use to interpret quantum mechanics based on observers, based on duality, based on your impossibility to understand the atomic realm. Doing that, look at this kind of statement based on the fact that you can pass continuously from Newtonian mechanics to quantum mechanics by just inserting in the theory a term for fluctuation and a term for dissipation. Think if it's reasonable to assume that you have an external element that will change the experimental outcomes when it interacts with the system, and etc., etc., etc. I won't go on that one again. Okay, this is for you to think about. I will do the same that Rony has done and pass to you some works to do at home. This is one of them. Let me see if I can now present to you positions and fluctuations just to see how the particle moves. The particle moves on the configuration and the phase and the momentum space, and how it fluctuates for each quantum state. Let's assume this situation. I will put a little less number of points, of course, in the trajectory for us to go back home at some point of our lives. 4,000 points, I think, will be sufficient. So look at these screens here. I think it will be interesting. Look at the size of the fluctuations. Let me insert here some delay in terms of microseconds. I don't know if this is working, but okay. Yeah, it's working. Not the way I would like to, but let's put more microseconds here. Let's see if this is good enough. And let's see a little bit, a greater number of points in the situation. Very good. Look the size of the fluctuations. This is important. And look how the movement in P is very random, while the movement in X is not that disturbed. Okay, let's do now. Yeah or not? Oh my God, I think I put too many points in the trajectory and the problem just ended. I remember that I put a restriction here that after some number of thousand points in trajectory, it stops showing. Sorry, we will have to wait until this ends. But doesn't matter. What I want to show to you here is that if I get greater quantum mechanical states for the same physical system, which is here the harmonic oscillator, what you get is just the increase of the strength of the fluctuation, because greater states show stronger fluctuation behavior, and you will see that the movement in P becomes quite, I will say chaotic, but not in the physical sense. Chaotic because it's too much random in this sense, the usual sense, common sense. Oh my God, this will take a lot of time. I don't believe that I did that. Well, so let's recollect what we have already obtained. We have shown that quantum mechanics has an stochastic support given by the Langevin equation. And when this Langevin equation is based on a fully corpuscular approach, of course, in these realms of mechanics and physics, there is no discussion about the fact that the Langevin equation is related to particles, point particles, which of course has a random behavior and dissipation. We have seen that because we can make simulations, which we are now seeing, we can show that the particle behavior can, in a time window, represent the probability density function that we get from quantum mechanics. This means that we can interpret quantum mechanics based only on a nature made of corpuscles, particles. And of course, the probability density function, which is composed from the psi, is just the outcome of our look, our analysis of the entire movement of the particle in the single system approach, of course, and if we are on the ensemble, of course, the collection of equally prepared systems. So let me see if I can just stop this thing so that we can go on. I will run it again. So I will share the screen with you. Just a moment, I will run the application again. So I will be able to show the screen with the simulations again. Now it will be quicker to appear. Let me present to you, because we will be waiting for the eternity to see the results of the fluctuation. So let me use the pace. The pace was good. 1,000, I think it's enough. I won't change much of these results here. We'll put just 40,000 points. Or 40,000 or 10,000. I'm afraid. 10,000 points. And single system. First, the ground state. Let's see the fluctuations on small. We have already seen that. Just seeing it again. This is the behavior of the system. And now let's see for the, come on. Well, at least now it will be quicker. I think it is just for 4,000 points. Whatever. I will put less points here. Okay. Let's put just 4,000 points. Will be enough. So let's see for n equal to 1. Let's go one by one. I have to change this. 4,000. Okay. Look what happens. Okay. And you have the same behavior for greater states. Fluctuations go more and more strength. Yeah. Well, let me see if I have any more thing to show you. No, I don't think I have. Well, we could play with these systems more than we have done, but I think it's enough for the time being. So with these results, I can assume that I show it to you that it's possible to, at least plausible, to make the interpretation that I was trying to put forward to you. And I hope that these classes that we will be attending will be of any profit to you. Thanks for your presence. I would like to say that our closing session will be held at 9 o'clock today, 9 o'clock p.m. and we count with your presence there. Thank you very much for watching. If there is any question, I will be glad to answer them. If not, I think we can end our interaction now. Okay, it seems that we don't have questions. I think it would be very interesting for you to think about the the tunnel effect. Now, using this interpretation will be very instructive, I think. It's interesting that no one has asked about this situation, but think about this if with what I have presented to you in these classes. Thank you very much, and I hope I can see you in the closing section. Bye-bye.